how we use reheat up here. So after we look at algorithms, we're going to implement it. We pass k in. K is an element. So we said we always look at a hole from our algorithms. Hole at this point is going to be at last index. Right there. So we said in hole equals last index. So give the index of the hole. Now we're going to have to keep this hole moving up, reheat up. That's based on the condition that when we move it up, because the element is greater than the parent, and hole mass 1 divided by 2 give you parent location. In this case, if it is greater, it's keep moving the hole up. And also, it could reach the root. When it becomes a root, then that means that new element has to set at the root. So that's why, based on these two conditions, hole has to be greater than 0. So it's going to keep moving that hole up by elements.set. So this part pretty much just take the parent's values that's less than the new elements and set it into the hole and move the hole up into that parent's location. So change the index of the hole. So keep doing that until one of these condition is not compiled. So we're going to say that is the location for new elements. Right. So element.set, we move k to the hole. Now let's look at DQ. For DQ again, we have to check if it is empty. Since this is using an array, so that's why we have to do that. So if it's empty, then we don't want to DQ by checking last index equal to -1. So though exception PriorityQ is empty. So else we can start to DQ by removing the root elements.get at index 0 equals to hold. And we're going to return this back when we DQ. Return hold. Now, start to move. So first thing is we're going to put the elements to the most right of the root up. So we said elements.remove, which is the last index, right? The most right of the root of the tree, which is the last index. So we call .remove, and this remove has to do the move, just remove that node out. And it will return the elements to move, right? That's T type. So now we have the elements to move. These elements, after we remove, we have to decrement the size, last index minus, and we have to see that, hey, this is not the last element in the root. If it is, then it's done. So we check if this last index not equals to -1, because it could be last elements on the tree or in the heap. So if it's not, then we start to do operation reheat down. Because this remove already keep the shape property, now we have to make sure it's ordered properly by passing in the elements to move to reheat down. Now let's look at the algorithms for reheat down. For example, we DQ, we say we put a hole there. And we want to reheat down by, we know that the elements that we have is now E, right? We just take E from here to keep the shape property, so we have E here. So E start to compare to So first we have to look at if we should reheat to the left or right. So among these three, we know that J is the greatest. So we're going to move the hole down and put the J up. So again, E has to compare among F and A, right? So we see F is greater. So holes keep moving down. And again, E compares to B. E is greater than B, so we find the location for E. So we put E right there. So let's look at implementation now. So reheat down, we pass the elements, which is E that we just looked at. Initialize hole equal to 0. And then we're going to have to create variables to store index where hole should move to, because we keep moving the hole. And then we're going to create a method to find next hole. This method pretty much just compare the elements, right, to those two children. Who is the highest, then we know the next hole to move to. So while new hole not equals to hole, that means the location is not for it yet. Then we have to keep moving the hole down, right, and keep moving the values set, right, the values up like that. After we move the hole down, the values that we compare has to set back to the location of the hole and keep moving the hole down. So this is what it does here. So we set elements.set and pass the hole, and elements.get the new hole. Right, because we know that new hole is going to be that location J, so we're going to set J to the hole and move the new hole to the where J is. So this pretty much doing that. Move the element up, and then hole equals to new hole. Right, because operation new hole already compared them. And then we pretty much just do it again, right? This is the same operation, find the new hole again. Compare the values of among those three, right, elements. And then we get a new hole, so while new hole not equals to hole, then we keep doing that until last place where we said, hey, we compare E and hole. Hey, we found that hole is equals to new hole. We're not moving any hole. Then exit while loop and set the elements, which is E into the hole. So that's how we do the heap down. Now let's look at the operation of new hole. How are we implementing it? Right, like we said, this new hole, the whole thing is just to compare, should we move the hole to the left or right by comparing the elements to those three values, right? Itself and left and right, find the greatest. So now I take the elements and the hole. So we said if either child of hole is larger than elements, return the index of the larger child. That's what we want. Otherwise, return the index of the hole. Just find location of new hole. And we already know this is the index formula again to get the left and the right. Okay. Like for example, our hole now at the root, right? We said index formula, since we use an array, right? Hole times 2 plus 1 give you left, right? Hole times 2 plus 2 give you right, right? So if you go back to array, so this is we want to get the left of J. Holes times 1, hole index is 0 times 1 is 0, plus 1 you get the left, plus 2 you get the right. So that's the index formulas. Like for example, if I say I want to get the index of the left of H is 1 times 2 plus 1, we get 3. 3 is D. If we want to get right, just 1 times 2 plus 2, which is 4, G. So that's the index formula that we use here. You can review that in Chapter 8 again, but I just try to show you here. So that's how we get the left of the whole and the right of the whole. Then we can start to compare if left greater than the last index. So if left greater than the last index, that means whole has no children. Right? Because it's index out of bounds, right? Then we just return whole. Else, if this is just check that if this actually has children, right? Now, if it has no children, we return whole. So that we found location, which is the last, which is a leaf, right? That's going to put the new elements in. Else we start to check. Okay, it's not a there's a children, so we say if left equals to last index. In that case, that means we only have left child. We want to see if it has 2 children or just 1 child, right? So if left equals to last index, so that means it pretty much has left child only. Then we start to compare the values of the left child to its elements. If it's less than, that means it has to go down to where the left is. The element has to go there, return the index of the left. Otherwise, we just return the whole without a location to insert. Now, else in this case, it's not just 1 child. The whole has 2 children. So in this case, we have to see if it should go to left or right by comparing the elements to the elements that get left to the left. So pretty much just take the left and right, comparing them, and then we will see that if it's less than, then we have to, if left child is less than right child, then we have to move to the right. Correct? So it's going to return. It's going to compare it to its whole first. Take the right, compare it to the elements to see which one is the greatest, right? We compare ones left and right, and once we found the right, we take the right compared to the itself. Now, if it happens to be the right is less than, then the right compare and the right child less than, then we're going to say return whole. In this case, right child is less than elements. That means, hey, the element is greater than the right, the whole is greater than right, then we just put into the whole location. So that's why we return the whole. Otherwise, we have to return the right, right? New whole should go on the right. Alright, so else, in the else scenarios mean it has to move to the left, right? Because after we first compare left of the whole and right of the whole, we said else mean left child is greater than equals to right child. In that case, new whole has to move to the left. But before we move, we have to compare to the elements, right? So this whole logic is compare those 3 elements, right? So we compare to its elements, and we found that if the left child less than the element, that means element is greater than the child, then return the whole. Otherwise, we return the left. Right? Because if child is less than the left, then we found a new whole, then return left. So that's pretty much it, right? This is compare among 3 in the case of has 2 children. And this is to make sure that it's not the last index, not the last node in the root. If it is, just return the whole. And this is to make sure that it's not just 1 left child. It's always going to be 1 left child, there's no 1 right child, because the shape property has to be complete.